Welcome to our deep dive into a topic that's sure to make you think, well, deeply. Today, we're diving into modal interpretations of quantum mechanics.
Ah, yes, modal interpretations. These interpretations are fascinating.
They really are, especially for anyone who, like our listeners, enjoys philosophy.
Absolutely, because we're getting right to the heart of it.
To the heart of reality itself.
Yeah. And what it means for a property to be real in the quantum world.
In a quantum world, right, because we all know how strange quantum mechanics can be.
Oh, it's definitely strange. What's so intriguing about these interpretations is that they're trying to bridge that gap.
The gap between quantum mechanics and our everyday intuition, right?
Exactly. We're so used to things having definite properties.
Like, a ball having a definite position.
Right, or a definite momentum.
But quantum mechanics, it kind of throws a wrench in that.
It really does. It suggests that maybe these properties, they only become definite when we measure them.
It's like the universe is saying, I'm not going to commit to anything until you force my hand.
That's a great way to put it. So how do these modal interpretations try to tackle this?
Yeah. How do they address this strangeness?
Well, they do something pretty bold. They say, let's keep all the weirdness of quantum mechanics.
All the superpositions, all the uncertainties.
Exactly. But let's also allow for some properties to be definite.
Even when they're not being measured.
Even when they're not being measured, it's like having your quantum cake and eating it too.
That sounds too good to be true. Can you give me a concrete example?
Sure. Imagine you've got an electron.
Okay, an electron.
And it's in a superposition of spin states.
Classic quantum scenario.
Right. Now, standard quantum mechanics says its spin is undefined until you measure it.
Okay, so far so good.
But a modal interpretation might say, no, 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 that electron actually does have a definite spin.
Even before you measure it.
Even before you measure it. It's just that the quantum state, it's not telling us which spin is definite.
So it's not about getting rid of the superposition. It's more about saying there's something definite hidden within it.
Exactly. It's a subtle shift, but it's a profound one.
It really is. But wouldn't that lead to contradictions?
Contradictions.
Yeah. What about, for example, the Kochen-Specker theorem,
Ah, yes. The Kochen-Specker theorem.
which says you can't assign definite values to all properties at the same time?
Right, right. And that's where the real cleverness of modal interpretations comes in.
Okay, I'm intrigued.
They're not trying to assign definite values to all properties at once.
So they're picking and choosing.
In a way, yes. They pick out a special subset of properties that are allowed to be definite at any given time.
It's like a game of quantum musical chairs with only a few definite seats available.
I love that analogy. And the rule that decides which properties get those seats is crucial.
That's the actualization rule.
Exactly. Each modal interpretation, it has its own version of this rule.
And that determines which properties become definite in different situations.
Precisely. So we've got these definite properties hiding within the quantum superpositions.
And we've got an actualization rule deciding which ones get to be real.
Right. But how does this all tie back to the infamous measurement problem?
That's what I want to know. How do modal interpretations tackle that?
Well, remember, the measurement problem arises from that idea of the wave function collapse.
Right, when we measure a system and its state suddenly collapses.
Exactly. But modal interpretations say, wait a minute, we don't need a collapse.
Because we already have definite properties before the measurement.
Precisely. The measurement isn't creating definiteness. It's revealing the definiteness that was already there.
Hidden within the quantum state.
Exactly. So no need for this extra process of collapse.
It's definitely a more elegant way of looking at it. But how do we even know which properties are definite in the first place?
That's where the idea of a value state comes in.
A value state. Okay, tell me more.
Think of the quantum state like a map of a city,
Okay, a map.
showing all the possible routes you could take.
Okay, got it.
That's like the dynamical state in modal interpretations.
So the quantum state is the dynamical state.
Right. But you only actually travel along one specific route at a time, right?
Right, only one route.
That's your value state.
So the dynamical state is all the possibilities, and the value state is what's actually happening.
Exactly. The dynamical state encompasses all the potential properties, while the value state singles out the actual ones.
This really feels like we're peering behind the curtain of quantum reality.
I think so too. It's not just about probabilities anymore. We're talking about actuality.
Actuality's hidden until we measure them.
Right. And that brings us to the different flavors of modal interpretations.
Ah, yes. The different flavors. Tell me about them.
Well, there are different ways to choose that actualization rule and define the value state.
So each flavor has its own recipe for deciding what's real.
You could say that. Two of the most prominent approaches are the BDMI and the SDMI.
BDMI and SDMI, okay.
They use different mathematical techniques to select those definite properties.
So different flavors, different ways of picking what's real, but it's not just an arbitrary choice.
Right, not at all.
Ooh.
These different choices have different implications.
For how we understand the quantum world.
Yes, especially the relationship between the whole and its parts.
This sounds like we're getting into some deep philosophical territory here.
We are. It's the age-old question of wholes and parts, but with a quantum twist.
And I can't wait to hear more about it.
Well, let's imagine a simple example.
Okay, an example.
Like a table with a green left side.
A table, okay.
In classical physics, it's straightforward.
The table is green, the left side is green.
Right. But in the quantum world, things get a bit more complicated.
I have a feeling this is where the mind-bending really begins.
You're not wrong. You see, some modal interpretations, they have trouble making sure the properties of the whole and the parts are consistent.
So you could have a table with a green left side, but the left side itself isn't actually green.
That's the kind of conundrum we run into. It's like the properties of the whole are floating free from the parts.
This is definitely making my head spin.
But it's a good kind of spin.
It is. We've gone from questioning whether properties are even real to exploring all these different ways of understanding them.
And we've only just scratched the surface.
I can't wait to see where we go from here.
Welcome back to our exploration of modal interpretations. Last time we got pretty deep into how these interpretations try to make sense of those definite properties in the quantum world.
Without even needing that wave function collapse idea, right?
Exactly. And we even started to touch on that whole problem of wholes and parts.
Yeah, how some interpretations struggle with making sure the properties of the whole system match up with the properties of its parts.
It's a tricky business, for sure.
It really is. And it gets even trickier when you consider that the set of properties that get to be definite, well, they can actually change over time.
Yes. The dynamics of properties, that's a key point.
It's like the universe is constantly shuffling the deck of what's real and what's not.
A very apt analogy. So how do these interpretations deal with that? How do they describe how these definite properties evolve?
Yeah, how do they handle that change?
That's a question that's led to a lot of debate.
Oh, I bet.
Some argue that we need a separate set of rules, like a quantum traffic guide to explain how those properties transition from one moment to the next.
So we're not just jumping from one state to another, but there's a smooth flow.
That's the idea. After all, that's how we experience the world, right? As a continuous flow.
It's like watching a movie. You want to see smooth transitions between the frames, not sudden jumps.
Exactly. And this need for a smooth narrative, it suggests that just specifying which properties are definite at each moment might not be enough.
We need something more to connect those moments together.
That's what some argue. We might need a more, how should I say, robust account of how those definite properties change over time.
So, are there any interpretations that actually try to do this? Provide this dynamic account.
There are. And it's an active area of research. Some explore the idea of transition probabilities.
Transition probabilities.
Yes. It governs how those properties change from one moment to the next, like adding traffic lights and speed limits to our quantum city map.
I like that image. But it also sounds incredibly complex.
It is. One of the biggest challenges is that the set of definite properties, remember, it can change over time.
Right. We're not dealing with a fixed set.
Exactly. So you need a way to connect properties at different times, even when the cast of characters is changing.
It's like trying to write a screenplay where the number of actors on stage keeps changing, but the story still needs to make sense.
That's a great way to put it. It's a real challenge.
It is. It makes me wonder if maybe there's a simpler approach.
A simpler approach.
Yeah, maybe we don't need this elaborate choreography of property transitions.
Interesting.
Maybe it's enough to just say which properties are definite at each moment and leave it at that.
That's a view some hold, actually. They argue that specifying properties at each instant, like taking a series of snapshots, is enough. We don't necessarily need to track every single change in between.
It's like saying to appreciate a symphony, you don't need to analyze every note, every transition. The overall experience of each moment is what matters.
That's a good way to think about it.
But it does make me wonder if we're losing something by giving up on that more detailed account.
A valid point. It's a debate about the nature of time and change, really.
Makes you think. But maybe we can shift gears a bit.
Shift gears.
Yeah. I'd love to hear about an interpretation that takes a totally different approach to properties.
Oh, you mean the perspectival modal interpretation?
PMI. Perspectival, that sounds intriguing. Does this mean properties are like observer-dependent in this view?
In a way, yes, it suggests properties aren't inherent to the system itself.
But they're not intrinsic.
Not in this view. They're defined relative to other systems, like saying the location of a book only makes sense relative to the table it's on, or the room, or even the earth.
It's all about relationships.
Precisely. It's about context. It actually shares a lot with relational quantum mechanics.
Oh, I could see that. Both emphasizing the importance of relationships and interaction.
Exactly. They both challenge that idea of absolute context-independent properties, but PMI takes it further.
How so?
It gives specific rules for how these relational properties are determined.
So it's not just a philosophical idea, but it has mathematical rigor.
Exactly. It's a concrete interpretation.
Can you give me an example?
Sure, let's go back to the EPR experiment. Those two entangled particles separated by a huge distance.
Right, the classic EPR setup,
From the perspective of one particle, the other particle's properties are well defined.
even though they're far apart.
Yes. It's like each particle has its own view of the other's properties, shaped by their entangled relationship.
So what's definite depends on your perspective.
You could say that. It's a very local and contextual account.
It really challenges our classical intuition.
It does, but it's also very elegant and consistent with that relational nature of quantum mechanics. Makes you wonder if that spooky action at a distance even exists in this view.
Right. What happens to that?
Well, it depends what you mean by spooky. PMI doesn't deny those correlations between distant systems.
But it's not some mysterious force acting across vast distances.
No, it's about the connection, the relationship between those systems. Like they're connected by an invisible thread woven from their shared history.
The power of relationships, even in the quantum world.
Exactly. But before we get too carried away with PMI, I'd love to touch on another interpretation.
Another one. There's so many.
There are. A particularly interesting one is the modal Hamiltonian interpretation, MHI.
MHI, okay. What's so special about this one?
This one gives a special role to the Hamiltonian of a system.
The Hamiltonian. That's the operator for the total energy, right?
That's right. Now, in most interpretations, the Hamiltonian's job is to describe how the quantum state evolves over time. Like the conductor of an orchestra.
Guiding the music.
Exactly. But in MHI, the Hamiltonian does even more.
Oh.
It's like the kingmaker for definite properties.
The kingmaker. What do you mean?
The actualization rule in MHI, it's based on the symmetries of the Hamiltonian. Any observable that shares those symmetries gets to have a definite value. The others don't. It's like the Hamiltonian sets the rules, and only properties following those rules are considered definite.
That's interesting. So it's a very principled approach to choosing the context for defining properties.
Very much so.
But how does this interpretation handle the measurement problem?
It does, but in a unique way. It addresses the measurement problem without relying on decoherence.
Decoherence. Can you remind me what that is again?
Sure. It's that idea that the interaction of a quantum system with its environment, it destroys those delicate superpositions. It's like the environment is constantly measuring the system.
Forcing it to pick a definite state.
Right. And many interpretations use decoherence to explain why we don't see macroscopic objects and superpositions.
Because the environment has already collapsed their wave function.
Exactly. But MHI offers a different perspective. It argues that the Hamiltonian itself, especially in large systems, acts like an internal environment. It can essentially decohere the system itself.
So no need for an external environment to do the dirty work.
That's the idea.
That's fascinating.
Yeah.
But all this talk of definite properties and actualization rules, it makes me wonder, what about probability?
Ah, yes, probability. We can't forget about that.
Quantum mechanics is inherently probabilistic, but how does that fit in with all these definite properties? Are we sneaking in hidden variables here?
No hidden variables here. Modal interpretations, they don't deny that inherent randomness, they embrace it. But there are different views on how to interpret probability itself.
So it's not just about whether things are definite, but also about what it means for something to be probabilistic.
Precisely. And that leads to some pretty intense philosophical debates.
I bet. So where do those debates take us? What are the different views on probability within modal interpretations?
That's a great question, and one we'll dive into right after the break. Stay tuned.
Welcome back to our deep dive. We've been exploring modal interpretations and how they try to make sense of the quantum world. It's been a wild ride, with all this talk of definite properties and different ways of defining what's real. But what about probability? Where does that fit in? We know quantum mechanics is all about probability, but how do modal interpretations handle that alongside their insistence on definite properties?
That's a really important question, and it takes us right to the heart of some big philosophical debates about quantum mechanics. You see, while all modal interpretations accept that quantum mechanics is probabilistic, they don't necessarily agree on how to understand probability itself.
So it's not just about acknowledging the randomness, it's also about figuring out what that randomness actually means. That sounds like a recipe for some pretty intense philosophical discussions.
It definitely is. One way to think about it is through two different views on probability: the actualist view and the possibilist view.
Actualist and possibilist. Those sound like some serious philosophical terms. Can you break those down for me?
Absolutely. The actualist view, which is often associated with interpretations like BDMI, SDMI, and even PMI, sees probability as a measure of our ignorance about the actual properties of a system. It's like saying a coin already has a definite side facing up, but we just don't know which one until we look. The probability reflects our lack of knowledge, not a lack of definiteness in the coin itself.
So it's kind of like an epistemic interpretation of probability
Yeah.
based on the limits of what we know about the world.
Exactly. It's saying the randomness we observe in quantum mechanics might not reflect some fundamental indeterminacy in the universe itself. It's more about us as observers being limited in what we can know about a system at a specific time.
That makes sense. But what about the possibilist view? How's that different?
The possibilist view, which is a prominent feature of the modal Hamiltonian interpretation, takes a more radical approach. It suggests probability isn't just about our ignorance, but about inherent tendencies or propensities of certain possibilities to actually happen. It's an ontological interpretation built into the very fabric of reality.
So instead of saying the coin toss is determined when we look, the possibilist view might say there's an inherent tendency, a sort of quantum leaning, towards heads or tails built into the universe from the beginning.
Exactly. It's like the universe is playing a constant game of chance, and the probabilities we observe reflect the rules of that game, rules that are woven into the very structure of reality.
Now, this is really making my head spin. We're basically being asked to choose between two very different pictures of the universe. One where randomness is a reflection of our limited knowledge, and another where randomness is a fundamental ingredient in the cosmic recipe.
And the choice between those views has some pretty significant implications for how we understand reality itself. If probability is ultimately epistemic, then there might be a deeper level of reality where everything is definite and determined. But if probability is ontological, then the universe is fundamentally open and indeterminate, even at its most basic level.
It almost feels like that old philosophical debate between determinism and free will is playing out on a quantum level.
That's a fantastic analogy. And what's interesting is that these two views, actualism and possibilism, aren't necessarily mutually exclusive. They could be seen as complementary perspectives on the role of probability in shaping quantum reality.
So, like two sides of the same quantum coin. On one side, probability reflects our limited knowledge about a definite reality, and on the other, probability is an expression of the inherent propensities of the universe itself.
That's a perfect way to put it. And it highlights the richness and complexity of the philosophical landscape that modal interpretations open up. They really force us to confront some of the deepest questions about the nature of reality, the role of observers, and the very meaning of randomness.
It's been quite a journey. We started by questioning whether properties are even real in a quantum world, and ended up exploring all these different ways to understand them, delving into the dynamics of properties, the idea of a perspectival reality, and even the role of the Hamiltonian as a kind of internal decoherence mechanism. And now we've ended up grappling with the meaning of probability and what it tells us about the universe itself. What a deep dive it's been.
And it's important to remember that while we've explored many ideas, the conversation around modal interpretations is still ongoing and evolving. There are many open questions and challenges that philosophers and physicists are still working on.
So the journey continues. It feels like the quest to understand quantum mechanics will keep leading us to even more profound and mind-bending insights about the nature of reality. To everyone listening, keep questioning, keep exploring, and keep diving deep into the mysteries of the universe. It's been a pleasure exploring these fascinating ideas with you.
Until next time.